So now I am going to the configurations, the different configurations. The transistor has different configurations based on our requirement. The requirement we will set based on our application. It is for the amplifier or logic circuits, that means a switch. So there we will decide that which types of or which configuration we should use. This is the common base configuration where the base is basically common in both input and the output loop. You see the input and output loop, the base is common, and it will be common means it will be grounded, right? Next is the common emitter. That emitter is common in both the collector and the input and output loop. You can see that it is connected with the collector through this bias, and this one also. Here I am not showing the resistance should be given, so this resistance will protect the transistor, so that's why we are using. So this is the common emitter configuration, and obviously the emitter will be grounded here. Okay. Next, the common collector. In case of common collector, there it will be, see that collector is common both in input and the output. Here you see that collector is common in both cases. So that is the for NPN and PNP transistor. So I think it is self-explanatory. So we don't want to discuss more. That means the collector is now here the grounded, right? So that is the common collector mode. So now the comparison of performance of different configuration. From there we can select for which purpose we will use the which configuration. That means in the circuit board, right? So the input impedance for common base configuration is very low. Common emitter it is low, but in common collector it is very high. Now if you see the gain, the voltage gain means the amplification, related to the amplification. Common collector is very less, so that's why we cannot use for the amplification purpose the common collector configuration, but it's a common emitter, it is maximum, so we can use for amplification, the sound, the audio amplifier which we have seen get the sound, there we are using the common emitter configuration, okay, generally. And then the phase angle, you can see for the common emitter there will be the change, 180-degree phase difference will be there. So that is basically the different, the different part, and based on the applications we will decide that which configuration we will use for which purpose. That we will decide based on the our requirement, I told, based on their these characteristics. So that's why I've just given here to understand that suppose I need the high frequency applications, then what we should do. So that is, we have to decide based on the applications that which configuration we should use. Okay. So now next is the common base configuration. So common base configuration, that this is the required circuit diagram. So here we will discuss the input characteristics and the output characteristics of the configuration, that is the common base configuration. Now please see the circuit. If you will just see the circuits, then you will feel yourself that what is it is a very complicated circuit, right? But what is the happening here? You can see that this is the NPN transistor because the arrow is outside. The base is common, that's why it is grounded, I told you, and it is common in both input. This is the input, this is the output. So the VBE is the input, base to emitter voltage, and the resistance, this is the emitter resistance. So we will apply here the Vin, that is the VAC which we want to amplify, and we will get the voltage from in the collector end. So this is the collector V out. Okay, so this is the collector resistance, this is called the emitter resistance, and this one is the base. Okay, so base is connected to the ground. Now for a particular voltage in VCB, that means collector to base, we have to consider like VCB is equal to 0 volt, or we can give the 8 volt or 18 volt. Then we will get different curve, and the different curve between the VBE with the IE. IE is the input current emitter. So in the emitter section, so here you can see that we will plot, and it looks like forward bias. It is a forward bias, so it is a like the forward characteristics of a diode, right? So when I increases rapidly with VB, and you know this is a silicon, so the threshold or the cut-in voltage we can get it 0.67 volt, right? So this is okay. I think it is clear for you. Now what the informations we will get from this curve, that is here the input resistance. One is the input resistance. So the input resistance, basically the ratio between the base to emitter voltage with IE, that is the emitter current, with VCB constant. So that means from here we can find out this, that is the straight line in the linear part we should consider for getting this. And here we can get the amplification factor AV in the input level, that is VCB by VBE with IE constant. So that is called the amplification factor, and this amplification factor is basically given from this curve. So in between these two, you can see when we will consider the two VCB, two collector to base different voltage, then what will be at one particular point, then the IE constant, that means the current is constant, then we can get the amplification voltage amplification factor, right? So it is clear, I think. Now we will go for the output characteristics. So what is output characteristics? That is basically the output characteristics. This side is collector to base and this side is collector current. So if you will go to this circuit, that when we will do the output characteristics, that means the input voltage and the input current will be fixed, it will not change, and there will be the relation between the collector to base with the collector current, right? So that is the output characteristics what we know, and there the current will be the fixed, the input current, that is the emitter current, will be fixed. So here you can see the hashed part is showing the cutoff region. It is mentioned the cutoff region. There is a three distinct region. There is another region which I have not mentioned, but three distinct region. One is the saturation region. This part is the active region from here to arrow up to this, and this hashed part is basically the cutoff region. So when the voltage, when the current, the emitter current will be less than 0, at that time what is we are observing, that is basically the cut-in voltage. So it is a switch. For the switch action we will use the transistor in this region for the switching part. And here what we have seen, that first it is linearly increasing, so it is a ohmic region, that part is called the saturation. Okay, but after that when we are increasing the collector to base, that means the output voltage, the collector current will not increase drastically, and here very small variation, but it is almost parallel to the x-axis, that means the voltage axis. So this part is we are using, our important part is this active region for amplification. So please understand, when we will use the active region, that part is basically responsible for giving us the amplification, and we will discuss in the later slide, and this part is for the switching action. Okay, so I think you will not forget it. Okay, next, what is the informations we are getting, that in active region IC is approximately equal to IE, you see. Okay, IC means the collector current, equal to IE in the active region, almost same, IC and IE. Okay, and next, what is the things that if we can use this for another, that IC increases slowly due to the VCV increasing in the active region. Okay, so next, in active region, it is already nearly flat. What I discussed, it is just given here, which signifies output resistance in this configuration is very large, right? In saturation region, I told you that it is linearly increasing. So the VCV results in a large increase in the collector current. If I made 0, that I told you that the hatched part, this is basically the leakage current. There is a very small current and you can say it is almost 0. So this current is basically we can ignore, then we can use for the switching action. Okay, this is a leakage current, but we cannot, in real devices we will get this current, so we cannot ignore. That is the reverse saturation current. In case of diode also, we know that reverse saturation current is very important. So this is the reverse saturation current. Okay, so the common emitter configuration with NPN transistor. Now the previous one, it is a common base configuration output characteristics. Now we are switching to the common emitter configuration with NPN transistor circuit diagram. Here you can see that NPN transistor, this is the circuit diagram which we are using in the circuit for understanding the characteristics. The emitter part is common, you can see in both input and output, I told you, and this is grounded. Here it is not showing, but this is grounded. IE is the grounded, I mean the emitter lead. This one is the base to emitter voltage, the potential. This is the collector to base, and this is the collector to emitter. So these are the basically the 3 voltage components, right? And this is the input bias, DC bias, and this is the output DC bias. Here we are using the, for the collector, you can see here we are given more. That means from here we can conclude that the bias, the applied bias is more in case of the output region. So the one is the Kirchhoff's current law. According to the Kirchhoff's current law, we know the IC is equal to IE, IE is equal to IC plus IB, and IC is equal to beta IB. What is beta? Beta is the common emitter current gain. Okay, common emitter current gain defined as beta. Okay. So the NPN common emitter circuit, this is the output characteristics. You know these things. In the output characteristics, it is just looking like this. So here I am showing the breakdown region also. The breakdown region, here you see that IB, if you go to the previous slide, then you can see here the IB is the base current, is the input current in this case, and the input voltage is the base to emitter voltage. Similarly, here you can see the collector to emitter voltage is output voltage and output current is the IC, and I is obviously 0. So this is the things, that's why you can see here the with fixed IB we will get the different part, the saturation, active, linear, and the breakdown. Breakdown means after some time, you know, that it is in reverse bias. So when the huge current will flow at a time, then we will get the breakdown. So that is the breakdown region. And this one, the hatched part, is basically the cutoff region, you know, that is below the IB is equal to 0. So here the base current is as a parameter we are using. Okay, so this, what I told you, it is given here exponentially, the same explanation. So whatever I told you, the same is just given here. Next, the common collector configuration, where the common collector configuration, we will give the output, we will get the output here, and we will put the input here. The collector will be common in both. So here you can see that the this is the output voltage, and it is NPN transistor. So the collector current, this is the collector part, so it is common in both the emitter as well as the base. Okay, so here you can see the active region, the saturation region, and the cutoff region the same way, but the IB, that means the base current, is as input here. IE is the output current, okay, and because IC is the here grounded, right? The IC is basically grounded. So this one is the IC, the collector is this one, right? This is the emitter. So the primarily used for the, I told you that the voltage gain amplification is less than 1, the voltage gain is less than 1 in case of common collector. So we are using this for impedance matching purpose. We will discuss the different applications of BJT. There I can tell you the common collector circuits we will use for the impedance matching, means we need the unit gain. There for the power, we will use the power transistor. There we are using the common collector configuration, okay. So we don't bother about the voltage amplification, there we can use the things. Now the current gain, these equations are very important. Alpha is the amplification, the current amplification factor when you have the base, common base configuration, that is, okay. And this one is the beta, is basically the common emitter configuration, current gain, and this is the Kirchhoff's current law, you know. And this one is basically the IB, is basically the base current, so we can just write this. So these equations are basically, you can also derive yourself if you try. Gamma is the common collector current gain. So this alpha, beta, gamma. Beta, again I am repeating, beta is the common emitter current gain, okay. So this is the common emitter current gain, this is the common base current gain alpha, and gamma is the common collector current gain, okay. And the relation between these three is just here, you can also try yourself, you can also derive the same, okay. So the ratio of the number of electrons arriving at collector to the number of electrons emitted by the emitter is called the amplification factor at common base. So that is basically, I told you, this is the alpha, okay. Alpha is the fraction of electrons diffuse across at narrow base region. 1 minus alpha is basically the fraction of electrons that recombine with holes, because you know that maximum will be 1. So alpha 1 minus alpha is basically the fraction of electrons that recombine with holes and the base region to create the base current, right? So the value, the alpha value is basically 50 to 500. The common base current gain is 50 to 500. I already discussed the current gain, you can check also there the table. So it is the same, and the beta is 0.99. So beta value, that means common emitter current gain, it cannot exceed 1, okay. So that is the typical value which we can use for our understanding, okay. So when we will proceed for any kinds of problem solve, so for that you should know, you should aware with these parameters, because these are very common parameters. Now I am giving some of the examples, the exercise, such that you people can understand that the how we can do these things. So the determine beta DC, you see beta DC means the common emitter DC current gain, okay. And IE is the emitter current of a BJT, where IB is providing, IC is providing. How we can solve? This is the circuit diagram, this is an NPN transistor, you know, this is the VV. So here it is a common emitter configuration. So common emitter means the base current IB is basically input. So beta DC, how we can find out the beta DC? It is very easy, IC by IB. So we have to find out IC. IC is given, IB is given, so you can easily find out beta. So there is not a big problem to find out the beta DC, okay. And it is 73. We already know that from 50 to 500 the beta value will vary, okay. Next is the, what we have to next find out? IE. IE is easy, IC plus IB, you know, IB plus IC is equal to IE. So we will just do these things, then we can find out the IE. So it is very easy problem, I just given you to understand that what will be the current and emitter current, which is basically, but you know that emitter current is here, it is grounded, but we have to get it, that's why we have to just show these things, okay.